Right now, billions of invisible particles are crashing into your skin at roughly the speed of a jet plane. You feel that constant bombardment not as a sting, but as the air around you. These tiny, flying specks are what we call a gas. We are going to uncover what a gas actually is, by picturing it as a swarm of tiny, fast-moving particles. We will see how these particles are spaced and how they move, and then use that picture to understand why gases can be squeezed, why they push on things, and even try a simple experiment with a syringe to make it all click. A gas is one of the three main states of matter, alongside solids and liquids. Imagine it as a collection of incredibly tiny particles, either single atoms or small groups of atoms called molecules, that are widely separated and zipping around independently at very high speeds. Because they are so far apart, a gas will always spread out to fill whatever container it is in, no matter the shape or size. To really see the difference, let's compare the three states. In a solid, the particles are packed tightly together, like people in a crowded elevator, and they can only vibrate in place. In a liquid, the particles are still touching, but they can slide past each other, like a flock of sheep moving through a gate. But in a gas, the particles are very far apart, with huge gaps of empty space between them. They fly in straight lines until they bump into another particle or the walls of their container. This is why a gas is mostly empty space. Because a gas is mostly empty space with fast-moving particles, it behaves in three very important ways. First, it can be compressed, you can squeeze the particles closer together. Second, those constant collisions of particles against a surface create pressure. It is like a never-ending rain of tiny ping-pong balls pushing outward. Third, since the particles are free and moving, a gas will always expand to completely fill any container. These ideas explain everything from why a balloon inflates, to how the wind blows, to how your lungs pull in air. Let's make this real with a simple syringe. Imagine a sealed syringe that is half full of air. When you push the plunger in, you are not squashing the air particles themselves, they stay exactly the same size. Instead, you are forcing them into a smaller space, so they are now closer together. Because they have less room to fly, they hit the walls of the syringe much more often. This increase in collisions is what you feel as a higher pressure pushing back against your finger. The particles are just as tiny as before, but they are now a much busier, more crowded swarm. If you heat a sealed can on a stove, it can explode, not because the metal melts, but because the invisible particles inside start hitting the walls so hard that the can gives way. A gas is a swarm of tiny, flying particles, and when you turn up the heat, they speed up and slam into the walls with more force. That force, spread over the inside surface, is what we call pressure, and it can be powerful enough to burst a metal container. In this video, we will meet the four knobs you can turn on any gas: pressure, volume, temperature, and amount. We will give each one a simple, physical picture so you can see what it really is, then we will show how changing one knob affects the others. By the end, you will understand why these four ideas are the complete set of controls for predicting how a gas behaves, and you will avoid the two biggest mistakes beginners make. Let us define each pillar with a simple analogy. Imagine a box full of bouncing rubber balls. Pressure is the total force of all those balls hitting the walls, spread over the area of the walls, like 1,000 tiny hammers tapping the inside of the box every second. Volume is just the size of the box, how much space the balls have to fly around in. Temperature is a measure of the average speed of the balls. The faster they move on average, the hotter the gas. Finally, amount is simply how many balls are in the box. Chemists count particles in a unit called the mole, which is just a very big number, about 602,000 billion particles, a convenient way to count atoms and molecules. To see how these four variables work, picture that same box of bouncing balls. Now, let us change one thing at a time while keeping everything else the same. If we shrink the box, reduce the volume, the balls have less space, so they hit the walls more often, and the pressure goes up. If we heat the gas, raise the temperature, the balls move faster, hit the walls harder and more often, and again the pressure rises. If we pump in more balls, increase the amount, more particles are hitting the walls, so pressure increases. In every case, we can predict exactly what will happen because we know which knob we are turning. Why does this matter? Because these four variables, pressure, volume, temperature, and amount, are the complete set of knobs you can turn on any gas. If you know 3 of them, you can calculate the 4th. This means you can predict exactly how a gas will behave when you squeeze it, heat it, or pump more particles into it. This is the foundation for understanding everything from car engines and refrigerators to weather systems and how your own lungs work. Mastering these 4 pillars gives you a superpower, the ability to see the invisible and control the behavior of gases. 2 common mistakes trip up beginners. First, confusing temperature with heat. Temperature is the average speed of the particles, a measure of how hot the gas is. Heat is the total energy transferred from a hotter object to a colder one. A spark can have a very high temperature but very little heat, while a warm bath has a low temperature but a huge amount of heat. Second, thinking pressure comes from particles pushing on each other. In a gas, the particles are mostly flying through empty space. Pressure comes from their impacts on the walls of the container, not from them squeezing against each other. Remember, the walls feel the force, not the particles themselves. You can crush a balloon with nothing but your bare hands and cold air, no pump, no pin, just temperature. But why does the same balloon swell in the sun? The answer lies in a hidden, 4-way dance happening inside every gas around you. We'll see how pressure, volume, temperature, and amount are connected, not as separate knobs, but as partners in a dance. We'll look at what that dance is, how flying particles make it work, 2 different ways to change pressure, and then use pure reasoning to predict what happens to a balloon in the sun, in the cold, and in your hands. Imagine a sealed syringe, a tube with a plunger, full of gas. Inside, pressure, volume, temperature, and the amount of gas are locked together. They are not independent. If you push the plunger in, the volume shrinks, and something else must change, the pressure rises. If you heat the gas, the temperature climbs, and again the pressure responds. These 4 are a connected system, like 4 dancers holding hands. When one moves, the others feel it. Pressure comes from countless tiny particles, atoms or molecules, smashing into the walls of their container. Each hit gives a tiny push. The total push over an area is what we measure as pressure. So anything that makes particles hit the walls more often, or hit harder, raises the pressure. Squeezing the gas into a smaller space crowds the particles, so they hit the walls more frequently. Heating the gas makes them fly faster, so each collision is harder. Adding more gas simply puts more particles in the same space, so there are more hits every second. That's the whole mechanism, frequency and force of collisions. Let's compare 2 different ways to raise pressure in our syringe. First, you push the plunger, volume goes down. The same number of particles are now in a smaller space, so they run into the walls more often. More collisions per second means higher pressure. Second, you heat the gas, temperature goes up. The particles gain kinetic energy and move faster. Now each collision packs a bigger punch, and they also hit more often because they cross the container quicker. Both paths lead to the same outcome, higher pressure, but the particle story is different. One changes how crowded they are, the other changes how hard they hit. Take a sealed, flexible balloon. First, it rests on a cold bench. The gas particles inside are moving slowly, they hit the walls gently and not very often, so the pressure is low and the balloon is a bit deflated. Now put it in hot sun. The particles absorb heat, their kinetic energy jumps, and they fly faster. They smash into the inner walls harder and more often, the pressure rises, and the balloon swells. Finally, take the balloon and squeeze it between your hands. You reduce its volume. The same particles are now crammed into a smaller space, so they hit the walls more frequently. Again, pressure goes up, you feel it pushing back against your hands. No math, just the particle story. What if a single equation could predict the behavior of every balloon, engine, piston, and breath you take? It all comes down to combining three simple patterns into one. Imagine you could write down a rule that tells you exactly how a gas will push, expand, or heat up, just by knowing four numbers about it. That rule exists, and it is beautifully simple. In this video, we are going to assemble the ideal gas law from the three gas laws you already know. First, we will see what the equation actually is and what each letter stands for. Then we will walk through how each term captures the dance of gas particles. After that, we will use it to predict real things, like a balloon rising or a can heating up. Finally, we will look at the number one mistake people make, so you never fall into that trap. The ideal gas law is written as PV equals nRT. P is the pressure of the gas, V is its volume, N is the amount of gas in moles, and T is the temperature. The new friend here is R, the universal gas constant. This one equation mathematically merges Boyle's law, which says pressure and volume are inversely related, Charles' law, which links volume and temperature, and Avogadro's law, which connects volume and the number of moles. It is the master rule for how gases behave. Let's walk through each term physically. Pressure, P, comes from the force of countless tiny molecules crashing into the walls of the container. Volume, V, is simply the size of the container, the space those particles have to fly around in. The number of moles, N, tells you how many particles you have. More moles means more collisions and a bigger push. Temperature, T, is a measure of the average kinetic energy of the particles, how fast they are zipping around on average. The equation balances these. If you heat the gas, the particles speed up, so either the pressure rises or the volume expands to keep the product PV equal to nRT. The ideal gas law lets you predict real behavior. Imagine a sealed can of air on a stove. The volume is fixed, so as the temperature rises, the pressure must increase. The equation tells you exactly by how much. Now think of a helium balloon rising into the sky. The outside pressure drops, so the balloon's volume expands until the product PV balances again. You can even calculate the new volume if you know the pressure change. This one equation unifies all those situations. The number one mistake is using the wrong units, especially for temperature. The ideal gas law only works if temperature is in Kelvin, because Kelvin starts at absolute zero where particles have zero kinetic energy. If you plug in Celsius, the math falls apart. The second big trap is picking the wrong value for R. R is a conversion factor that makes the units work out, and its number depends on whether you are using atmospheres and liters, or pascals and cubic meters. Always check that your R value matches the pressure and volume units you are using, or your answer will be completely off. What if I told you the air you breathe is secretly breaking the law? Not a legal one, but a scientific one that makes chemistry and physics far simpler. Every gas particle around you is a tiny rule breaker, and understanding that is the key to predicting how gases behave. We'll start by defining exactly what the ideal assumption means. It's a deliberate simplification about gas particles. Then we'll see how that simplification turns a messy real-world problem into one elegant equation. After that, we'll explore the two specific conditions where this model fails, and finally we'll work through a real calculation to see the breakdown in action. The ideal assumption is a model where we pretend gas particles are tiny points with absolutely no size of their own. They take up zero space. We also pretend they don't attract or repel each other at all, they're completely independent, like tiny, invisible, perfectly bouncy balls that never get sticky. When they collide, it's a perfect elastic collision, meaning they bounce off without losing any kinetic energy. It's a beautiful, clean, imaginary world that makes the math wonderfully simple. By removing particle volume, we don't have to subtract the space the particles themselves occupy from the container's total volume. The volume in the equation is simply the volume of the container. By removing attractive forces, we don't have to account for particles slowing down as they approach the walls, which would reduce the pressure. This means pressure is purely from the kinetic energy of collisions. All these simplifications collapse into one beautifully simple relationship: pressure times volume equals the number of moles times the universal gas constant times temperature. It's a single, elegant equation that ties all four pillars together. The ideal model breaks down in two specific situations. First, at very high pressure, you're squeezing the gas into a tiny space. Now the particle's own volume is no longer negligible compared to the container's volume, they're bumping into each other constantly, and the space they physically occupy matters. Second, at very low temperature, the particles slow down so much that even weak attractive forces become significant. They start to stick together, forming droplets. That's condensation. The ideal model imagines point particles that never touch. Real gases have finite size and get sticky when cold. Let's calculate the pressure of 1 mole of carbon dioxide gas at 300 Kelvin in a 1-liter container using the ideal gas law. Plugging in the numbers gives us about 24.6 atmospheres. But when we actually measure the pressure in a lab, we get only 22.3 atmospheres. The ideal law overestimates by about 10%. Why? Because at this high pressure, the co-molecules themselves take up a noticeable fraction of the space, and their attractive forces pull them inward, reducing the force they hit the walls with. The ideal assumption has broken down, and we can see exactly how much. A balloon in a hot car doesn't just expand, it pushes harder on the air around it. And the air in your tires? That's just a number you can calculate. Here's how one equation predicts both. We'll start by seeing how the ideal gas law connects pressure, volume, temperature, and amount. Then we'll walk through a simple 3-step method to solve any gas problem. After that, we'll use it on a hot balloon and a car tire, and finally, we'll dodge the 2 mistakes that trip up almost everyone. The ideal gas law is written as PV equals nRT. It's a single relationship that ties together the pressure, volume, temperature, and number of moles of a gas. The capital R is a measured number called the universal gas constant. It's the same for every gas, and it makes the units work out. Think of it like a recipe. If you know 3 of the ingredients, you can always find the 4th. Solving any gas problem follows 3 steps. First, write down the base equation, PV equals nRT. Second, use algebra to get the variable you want alone on one side. For example, if you're after pressure, divide both sides by volume to get P equals nRT over V. Third, plug in the numbers with their units, and let the units cancel to check your work. Let's try it with a balloon left in a hot car. Suppose it starts at 25 degrees Celsius and 1 atmosphere, and the car heats it to 50 degrees. We want the new pressure. Since the balloon can stretch, the volume stays roughly the same, and no gas leaks out, so N is constant. We rearrange to P1 over T1 equals P2 over T2, convert temperatures to Kelvin, and solve. Now let's find how many moles of air are in a car tire. A typical tire pressure is about 35 pounds per square inch, but our gas constant uses atmospheres, so we convert 1 atmosphere is 14.7 psi, so 35 psi divided by 14.7 gives about 2.4 atmospheres. The tire volume is roughly 10 liters, and a cool morning temperature is 15 degrees Celsius. We must convert that to Kelvin by adding 273, giving 288 Kelvin. Now we isolate N. N equals PV over RT. Plugging in, we get 2.4 atmospheres times 10 liters, divided by 0.0821 times 288 Kelvin. The units cancel to leave moles, and the math gives about 1.0 moles of air. That's around 29 grams of air, which makes sense. A tire holds a noticeable but not huge amount of gas. Two mistakes catch almost every beginner. The first is using Celsius or Fahrenheit for temperature. The ideal gas law only works with an absolute scale, because the pressure of a gas really does drop to zero at absolute zero. If you plug in 15 Celsius instead of 288 Kelvin, you'll get a wildly wrong answer. The second mistake is mixing units. The gas constant has specific units, like liter atmospheres per mole Kelvin. If you put pressure in pascals or volume in milliliters without converting, the units won't cancel, and your number will be nonsense. Always write the units next to every number and make sure they cancel to give you what you want. So the whole idea is, the ideal gas law is a powerful tool, but only if you speak its language: atmospheres, liters, moles, and Kelvin. Your lungs, a car engine, and a floating weather balloon all run on the same four-letter equation, and you probably use it thousands of times a day without realizing. Every breath you take, every car ride, every party balloon that escapes to the sky is a live demonstration of the ideal gas law. It is the hidden choreographer that makes gases dance to the tune of pressure, volume, temperature, and amount. We are going to take the ideal gas law off the page and into the world. First, we will see what the equation actually tells us about a gas. Then we will learn how turning one knob, like volume or temperature, forces the others to move. After that, we will walk through three rail machines: your own chest, a simple syringe, and a weather balloon. Finally, we will compare two very different cycles, breathing and a car engine, to see how the same law powers both open biological systems and closed mechanical ones. The ideal gas law is a single relationship that ties together everything about a gas. It says that pressure times volume equals the number of moles times a constant R times the temperature. Think of it as a seesaw with 4 seats. Pressure is how hard the gas particles push on the walls. Volume is how much space they have to fly around in. The number of moles, N, is simply how many particles there are. I counted in packs of 6 times 10 to the 23. And temperature is a measure of the average kinetic energy, the jiggle of those particles. The constant R just makes the units match up, like a currency exchange rate. The equation tells us exactly how the 4 knobs are linked. If you squeeze a gas into half the volume while keeping the temperature and number of particles fixed, the pressure must double. That is an inverse relationship: when one goes down, the other goes up. If you heat a gas in a rigid container, the particles jiggle faster and hit the walls harder, so the pressure rises. Pressure and temperature are directly linked. If you let a gas expand freely while keeping the pressure constant, it must get hotter. Volume and temperature are also direct partners. The number of particles, N, acts like an anchor. Add more particles and you increase the total push, so either pressure or volume or temperature must give way. Let us see 3 machines that use this law every day. First, your lungs. When your diaphragm muscle contracts, it flattens and pulls downward, making the chest cavity bigger. That increases the volume inside your lungs. With N and T roughly constant, a bigger V means a lower P. Now the pressure inside your lungs is less than the outside air, so air rushes in to equalize it. Second, a sealed syringe. If you hold your finger over the tip and warm the barrel with your hand, the air inside gets hotter. T goes up, N is fixed, and the plunger is free to move, so V must increase to keep P balanced with the outside air. The plunger slides outward. Third, a weather balloon. As it rises, the outside air pressure drops. The balloon skin is flexible, so the gas inside expands until its internal pressure matches the new, lower outside pressure. Now contrast two very different cycles. Breathing is an open system. The amount of gas, N, stays the same inside your lungs during a single breath. You are just changing the container size. Your diaphragm alters V, which changes P, and air flows in or out to balance it. An internal combustion engine is a closed system during its power stroke. The piston traps a fixed number of gas particles. Then the spark plug ignites the fuel-air mixture, causing a massive, near-instant temperature spike. With N and V initially fixed, P skyrockets. That huge pressure then pushes the piston down, increasing V. So in breathing, a muscle changes V to move air. In an engine, a chemical reaction changes T to move a piston. Both are just the ideal gas law rearranging its terms. The whole idea is that PV equals nRT is not just a formula, it is the rule book for every gas-powered machine, including you. We started with bouncing particles and ended with a single equation that predicts how every gas in the universe behaves. But the real magic isn't the formula, it's the four invisible assumptions that hold it all together. In this final recap, we'll pull the whole journey together. We'll see what the ideal gas law truly is, how its four pillars simplify the chaos, why this one equation is so powerful for making predictions, and what happens when we push gases beyond the ideal world. The ideal gas law, PV equals nRT, is a model that links the pressure, volume, temperature, and number of moles of a gas. The word ideal is crucial. It means we pretend the gas particles follow for very specific rules about how they move and interact. These rules aren't perfectly true for any real gas, but they're close enough to make the equation incredibly useful. The four pillars are what make the math simple. First, we treat gas particles as point masses. They have mass but take up zero space, so the volume in the equation is just the empty container. Second, we assume zero forces between particles. They don't attract or repel each other, so they only interact when they hit the walls. Third, every collision with the wall is perfectly elastic, meaning no kinetic energy is lost as heat or sound. The particle bounces back with the same speed. Finally, the motion is completely random in all directions. These four assumptions strip away all the messy real-world complications, letting us replace the chaotic dance of billions of particles with a clean, proportional relationship. The real power of the ideal gas law is prediction. Imagine you have a sealed, rigid container of gas, so volume and amount are fixed. You heat it from 300 Kelvin to 600 Kelvin. Intuitively, you know the pressure should rise, but by how much? The law tells you exactly, since V, N, and R are constant, P is directly proportional to T. Doubling the absolute temperature doubles the pressure. Without this equation, you'd have to simulate the paths and collisions of billions of individual particles. Instead, one simple calculation gives you the answer. But the ideal model has limits. Squeeze a real gas hard enough, and two of our pillars crumble. First, the particles themselves do take up space, so the actual empty volume is less than the container's volume. Second, at high pressures, particles are close enough to feel each other's attraction, which reduces the force of their collisions with the walls. The pressure is lower than the ideal law predicts. To fix this, scientists use the van der Waals equation, which adds two correction factors, one for the volume of the particles, and one for their stickiness. That's the next step in understanding how real gases behave.